Hello everyone, this is Terry Erzman. I'm the Chief Marketing Officer for Percona. Welcome to today's webinar. We will be making a recording of the webinar today, and we will make that available within the next 24 hours. Before we get started, I'd like to do just a quick sound check. If you can hear me all right, would you please raise your hand in the GoToWebinar control panel? And I see lots of hands going up. Thank you for that. Throughout the webinar today, if you have questions as they come up, you can enter them in the questions box in the GoToWebinar control panel, and we'll answer as many of those as we can at the end. But please enter them at any time, and again, we'll record the webinar and send out a link to the recording, and if we have more questions than we can answer today, Jay will write a blog post to answer any additional questions that come up. So with that, I would like to welcome Jay Janssen. He's MySQL consulting lead here at Percona, and today he is speaking on the hazards of multi-writing in a dual master setup. Jay?
Thanks, Terry. So hello, everybody. I guess just by way of introduction, I've been with Percona for about a year, and before that, I spent about 7 years at Yahoo, where I did a lot of MySQL high availability work and multi-data center deployments and things like that. And one of the things that typically came up there as people were discussing how to deploy their databases across multiple data centers was, well, if we simply set up what's called a dual master setup, and if you're not sure what that is, I'm going to go through that in detail. But if we set up a dual master setup in a couple of different data centers, then we can just configure our application to write to both of those dual masters at the same time. And it took some explaining to really get the concepts that I'm going to give in this webinar into people's heads, to get them to understand the complexities behind this, why you just can't do this, and it just doesn't magically work most of the time. It can work in some cases, but in a lot of cases it doesn't. So this talk is really going to be try to really be a high-level overview of the types of problems that you can see using a SQL database, specifically MySQL, specifically in a dual master setup, but really just in general, how these problems, what they look like in a multi-tenanted environment. So with that being said, I want to kind of jump in a little bit and explain some of the nuts and bolts of the problem, at least from the MySQL perspective. So in MySQL replication, there's some rules and things you need to understand. This might be introductory level for some folks, but really, again, I'm just trying to make sure the problem is really clearly understood. So a given MySQL instance can have some properties in terms of replication. First of all, it can be both a master and a slave. So you can see in our diagram we have a MySQL instance that both hosts as a master to the slaves on the bottom, but also has a master above it. It will have it can have 0 or 1 masters. So that MySQL instance cannot be multi-mastered on the top. Now there are some exceptions to that exist today, but I'm just talking for the most part now about straight up standard MySQL replication. So single MySQL instance can be a master and slave. It can only have 1 master or no masters, and it can have many slaves. Each of these servers in this replication topology are uniquely identified in their configuration using something called the server ID. And if you've ever configured this before, you know that this is just a number that has to be different on all of these servers in this diagram for replication to work properly, and more on what that does in the next slide. But beyond this, for replication, there's no other topological restrictions. So what's nice about this is it gives you flexibility to come up with some really interesting ways and creative ways to design a multi-server MySQL configuration for a lot of varying requirements and so forth. Now, when I say interesting, it's not necessarily just helpful ways that are interesting. There's also some really weird ways that come out, and there's some ways that can bite you. But generally speaking, there's nothing that really prevents you from doing a lot of complicated things as long as you can sort of link the servers together using these rules. In replication, there is no guarantee of replication lag, and you have to make sure you understand that. The write happens on the master, and then asynchronously gets copied to and applied to the slave. So there's nothing in MySQL that enforces that a certain transaction will be applied on the slave in some certain period of time. It's really all just fire and forget as far as the master database is concerned. Now there is semi-synchronous replication, which kind of gives you some guarantees here, and I'll talk a little bit more about that later on. But for these purposes, we're talking mostly about standard asynchronous replication, which is what most people use. The last thing I really want to make sure is clear about replication, and again, people who have done a lot of replication configuration in the past are aware of this, is that change master is a painful operation. Today, change master implies, well, you give it a few things, and you run it on the slave, and it instructs the slave about how to connect to the master database, and more specifically, where to connect on the MySQL, the master database, in reference to time. So when you configure a slave, you say, okay, well, the master is this host name, it's this username and password I'm going to log in with on this port, and it's a standard MySQL port. But then you also give it something called a binary log file and position, which is a sequential file of all the changes that have happened on the master, and those files rotate every once in a while, and then they keep growing as writes come into the server. So when you need to change from a single master to another master, doing that deterministically is hard because the binary log file and positions on separate MySQL instances are almost guaranteed to be different from each other. So what is the correct position in time and in the replication stream on one might not be the same on the other, and again, a little bit more on that later. So this is the overview of replication as it stands, and the basic rules that you need to know. So to take that into more of the core topic of our talk here, what does a dual master look like, and how does that fit in with the MySQL replication rules? Well, first and foremost, let me say that dual masters are useful for switchover and failover without having to do that painful change master. So if we have these two dual masters, master A and B, and one fails, we happen to be connecting to one, we can just change our application to point over to the other one, and we don't have to, can you see my screen? Terry, can you comment? I'm assuming you can. We don't have to
I can't see
worry
your
about
screen,
executing a change master command to. You can see it?
Yes, I can.
Thank you, Terry.
Sure.
Okay, sorry. I had another application interrupt me. So as I was saying, you can flip between one master and the other without having to re-execute a change master, and that's fundamentally what dual masters are useful for. And this is a lot of the type of architecture that we would set up and use at Yahoo, and is still in use today at Yahoo. So a dual master setup, quite simply, is two MySQL servers where each of those servers is both a master of the other and a slave of the other. And this, after you kind of wrap your head around that a little bit, it really isn't all that complicated. Each server can have exactly one master, the other server, and it can have many slaves. So there's nothing wrong with that, master A also slaving to master B, and then also potentially other slaves as well. Now, because this is circular, the transactions will be written on master A and then replicated over to master B, and then they will actually get replicated back to master A. But when it gets back to master A, the server ID of A will kick in, and it will compare any incoming replication traffic in those records is the server ID from the origin master, and it will compare that with itself, and if it sees the same server ID, it drops it on the floor. But it is important to understand that the writes on A would replicate to B and then back to A before they're filtered by the server ID. So important thing to understand. Now, let's shift gears a little bit and talk about writing into a database in general, and of course MySQL. So how do writes work on a single server? Take one of those masters that we have. Now in InnoDB, many people are, again, probably familiar with, but in InnoDB, when you go to make a change in a table, the rows that are getting changed are locked. The exclusive lock is taken as a transaction happens, and then as the transaction finishes on a commit, the locks are all released, and then some other transaction can come in and do some work. Now, also in InnoDB, you can do auto-commit equal 1, which just implies the end of a transaction after every statement. So row-level locking. Now, in my ISAM in MySQL, you've got table-level locking, and that's table-level exclusive locking for every statement that needs to modify a table. It has to go get an exclusive lock, the exclusive lock on the entire table for that statement. And the whole point of this is sort of, first-year computer science, but the whole point of this is that we want to make sure that nobody else can get the exclusive lock. That's why it's called exclusive. And until the first client who's going and doing his changes releases it. So the idea is nobody can write more than one at a time. The writes are serialized at some level. In MyISAM at the table level, in InnoDB at the row level. So sounds pretty straightforward, right? Now let's talk a little bit about how that applies to replication. And kind of the short of it is that it doesn't. So in a master and slave, you have the client. He connects up to the master, obtains the locks that he needs, lock or locks. He does his write. He finishes releasing the lock. Then, asynchronously, the write replicates to the slave. The slave SQL thread, which is the part of replication that applies transactions to the slave, it obtains the locks it needs on the slave, does the write, and releases them. So notice here that there is no point in time where these locks are taken by the same client on both servers. It's only taken on the master and then replicated down to the slave completely independently. So in a master-slave where you're only writing to the master, this is actually fine because there shouldn't be anybody on the slave who's writing or taking those locks or making any changes there that we need to be aware of. Now, let's take it a step further into our circular master or dual master configuration. All right. So the write is only the transaction, the update statement, the insert, whatever it is only locked on the connection that, or on the server that the client connects to. So whichever of these two masters that we have. The other master is lockless during the write, at least for that specific lock for that specific operation. So there's nothing preventing in conventional MySQL replication the same locks from being acquired simultaneously on the other master at the same time. So in the picture, client 1 locks row 100 on master A, client 2 locks row 100 on master B. Nothing prevents that in standard MySQL replication. So this violates the isolation attribute of ACID compliance. That is, that writes are done in isolation from anybody else doing writes. Specifically, anybody else doing writes to the same data. So that's kind of high-level theoretical. What does this actually look like? Well, now we'll get to the practical bit, and maybe this will make it a little more clear. So let's suppose we have two database servers, Percona 1, Percona 2, and these are configured in that circular replication dual master topology that I showed on a previous slide. So, Percona 1 replicates to Percona 2, Percona 2 replicates to Percona 1, and so forth. So let's take a situation where we've got a table with an auto-increment primary key I, and it has a data column J, which isn't particularly important for this exercise. So you can see at the beginning of each line, I'm indicating which server I'm executing these statements on. So at line 5 on Percona 1, I'm turning off auto commit. I'm starting a transaction. Line 6, line 7, I'm just inserting a row into the table with the value of Percona 1, so we know which one it came from. And then before I commit, so after line 7, that transaction is still open. On Percona 2, I'm going to go do this much the same thing and open up a transaction, insert the value of Percona 2, and hit commit both sides more or less at the same time. So what's going to happen here? And if I were doing this at a conference, it would be much easier for people to shout out the answer. But this is probably what you may have seen if you've done any of this before. You will see a duplicate key entry for the primary key on your show slave status. And not only will this be an error on Percona 1, but it will also be an error on Percona 2. So what's happened here? What happened here was that the next value for a primary key in a table is effectively achieved by taking a lock. It takes a lock and says, okay, give me the next primary key. There's different ways that works, but the basic idea is that the lock prevents other clients from taking the same primary key and using that. But because we're using dual masters and because we're using standard replication, nothing prevents that same auto-increment value from being taken on both masters at the same time, and then this leads to replication simply breaking. And the other fact about MySQL replication is that it is not self-healing. It's something that you have to go manually fix yourself, because really, what is a generic way to fix this problem if you've got two rows with the same primary key? It's kind of hard to answer. We don't know. Like, who should win? Should it be the latest one? Should they be separate somehow? So maybe to make that a little bit more practical, let's look at another example. So let's suppose we have our table T, but it's slightly modified now, and we have a username key or a username column, that is a unique key. So the idea is we want to make sure and use the database to enforce the constraint that no two users can have the same user ID, for example. So much the same way, we create that table, and then we have, let's just say we have two different users in there. So line number 6, we're inserting into table T. We're creating two users. Let's suppose this is a user table. So user 1, user 2. So that's all fine and good. That's not a unique key violation. We have two rows in the table. Now we start our experiment on line 8, Percona 1, and line 9. We're basically taking the user where the auto increment is 1, and we're setting his username, changing his username to Fred1234. So this is, imagine your web application. You're managing usernames, and somebody connects in and says, okay, great, I want to change my username. No problem. As long as the update succeeds, we should be fine. At the same time, somebody on Percona 2, who happens to be user number 2, goes and tries to do the same thing, and Fred1234 happens to be a popular username. So they both happen to do it at the same time, and they commit. What happens at this case? Well, the database doesn't complain because it has no idea that the lock exists on the other server. And also, to boot, we get replication breaking again. So we are unable to replicate this, the fact that both these users have this unique key constraint that breaks the SQL thread in replication on each side because there already exists a row there with that unique key. So what's the right solution in this case? Imagine your application, you have some website that maintains usernames. How do you resolve this? Which person should have that username and which should not, and how do you deal with it? It's likely a problem that you need to manage at the customer service layer, not something you can just generically arbitrate at the database layer. It's going to be way too confusing for people. So this starts to illustrate some of the problems. Now, these two examples we've seen, both of these break replication. Now, this example doesn't. So we go back to our table T, and we have, again, our columns I and J with the primary key. That's the auto increment. J is just a varchar. Straightforward. No constraints on J. So we insert a row into our test table with the value test1, and then we're going to perform our experiment where on Percona 1, we're going to set the value of J to Percona 1 for that specific row, and then on Percona 2, we're going to set the value to Percona 2 for the exact same row. So again, there's no locks, there's no sharing across replication about the fact that this is happening. So what's going to happen here? Well, replication isn't going to break, but you're going to end up with inconsistencies. So on Percona 1, when we go to look at our record, we're actually going to see the value of Percona 2. Now, that's not where we updated to Percona 2. We did that on the other server. On Percona 2, we're going to see the opposite. So what happened here is that these transactions crossed each other in midair, if you will, if in mid-replication stream, and were both applied successfully to the other side. Replication did not break, and you have no way to really detect this, at least from monitoring replication. You have to go back to using something like PT table checksum or some other way to validate that all of your dual masters and all of their slaves are consistent with each other. And of course, in this case, they are not. How do you fix this? It depends. It's completely application dependent. There's no deterministic SQL, answer in the relational system that describes how to deal with this problem. It's assumed that it doesn't happen. So what's the real issue here? The real issue here, if you kind of take a step back and think about it, is that we're intermingling our rights. We have simultaneous rights to two different masters, or let's just imagine a scenario where we have, n masters, 10 masters, who knows? And all of these rights are happening on all these servers at the same time, and then asynchronous replication is carrying those rights to all the other masters and applying them. What's going to happen is that each master gets a different order of transactions. So in our dual master case, we have master A and B. And if you look just at the first few transactions, we have transaction A and transaction A1 and A2 on master A, and transaction B1 on master B. If you look at the simple ordering of those in time, on master A, the A transactions happen first, and then B1. And on master B, B1 happens first, and then A1 and A2 happens, while those things are sort of crossing paths in the replication cycle. Now, that doesn't sound like a horrible thing as long as A and B are not interdependent on each other. So let me give you a final example. using the SQL method, where that really comes into play. So let's imagine, again, we have our table, and we have 3 rows in our table, each with a value of X for column J. So we have 3 rows in the column, or 3 rows in the table, rather. So in Percona 1, we start a transaction, and we update T. We actually updating all of the rows to set J equals to Y. At the same time, on the second server, we're going to insert a new row into the table. So this, to me, really clearly illustrates what's going to happen or why intermingled writes can be complicated. Update T can either happen before or after that 4th row with Z is entered. And let's see what happens in replication. Replication doesn't break again, but if we select star from T on Percona 1, we see that our statement from line number 7 happened before the insert on line 10 on Percona 1. So we have Y, 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 and then Z. But then on Percona 2, we have all Ys. And that's because the insert actually happened first on Percona 2, and then the update happened in line number 7. And again, this is because of the asynchronous nature of replication, and there's no locks, preventing these types of things from happening. So why is this a hard problem to solve? Fundamentally, what I would say is that isolation, the idea that while you're writing a piece of data, nobody else can modify that piece of data is an assumption that most people make when they write their applications. We don't like to try to think about what happens if somebody else actually modified the same data as we're doing at the same time. And pretty much everything in computer science is all about how to take locks and mutexes and so forth and do that very efficiently so that you can do serialized work as efficiently as possible in a concurrent environment. There's also this little thing called the CAP theorem. Now, I'm no, a PhD computer science person or anything like that, so maybe somebody could poke some holes in my thinking here. But the CAP theorem basically says that there's these 3 attributes: consistency, availability, and partition tolerance. And the idea of the CAP theorem is that you can have 2 of these, but you can't have all 3. So if you go back to our illustration of setting up dual masters, for availability, we're writing to both sides. We can take, multi-writing in this case takes availability, right? We're able to write to both sides, both databases. Partition tolerance, where, okay, fine, network breaks in between them, no big deal. But we're taking that over consistency. So we're going to lose consistency, but gain availability and partition tolerance. Now, you can argue about the CAP theorem and whether or not that's true, and whether or not, your favorite NoSQL solution solves the CAP theorem or whatever. But at the end of the day, this is a complicated problem, and a lot of really smart people have spent a lot of time thinking about this in a generic way. With the explosion of the internet, the more distributed our databases become, the more this has become up. Nobody really cared about this in 1970 in terms of writing to multiple data centers and so forth. So when can multi-writing actually work? I'm not saying that it can't work. Really, it's all about your application-specific workload and how you're using your database. So I'm going to introduce a term that I'll just call database entity isolation. And when I say entity, I mean it could be something as large as a schema, so a single entity meaning equaling one schema. It could be a table, it could be a row, some object inside the database. If we have isolation, and what I mean by isolation on that entity is that entity is only modified by either a single client at a time globally. So let's say that entity is a user, and the only person who can modify a user's properties is that user. So only one client at a time should be modifying that user anywhere in the world. Or let's just say that entity is only modified on one master at a time. Then multi-writing can potentially work. So that sounds like a really simple example, right? Okay, if everything's a user in our database, and the only people who can modify that record is a user, then and that user is in one location, then fine, we shouldn't have a problem here. But I think it's not quite as simple as that. It's easier to sort of say that your database has full entity isolation than it is to actually prove it. And the other thing I'd point out here is that relational data means that data is related or interrelated. So yes, you might have some entity isolation at the user level, but let's say you also have groups, and users belong to groups, and groups contain a set of users. Can you say that nobody is going to be modifying the group that a user is in more than one location, and what impact does that have? So the more relational the data is, the less likely that this is true, the less likely that multi-writing can work, even if you know that, okay, one user can only write to one database at one time. So perfect data isolation tends not to be realistic in a true relational database. And when I say a true relational database, I'm kind of thinking of the spectrum. There's a spectrum between sort of relational, third normal form, all these dimensions, users, groups, whatever it is, and they all have foreign keys and so forth. And then there's sort of pure non-relational data, which is just maybe raw data. It's a series of log data, that has no interrelationship with anything else, and is stored in SQL just before convenience or something like that. There's a spectrum between those two extremes, if you will, and your application may fall someplace along that spectrum somewhere. It really depends on what you're storing, how you're storing it, and the properties of your application, the application-specific knowledge of your application to say, will this work or will this not? It's very difficult for us at Percona as consultants. We come in and people ask us, well, can we just do this? And I have to, spell out very carefully, these are the types of things that can break. What do you see in your application that might fall into these categories? And I have to default on the safety side. I can't say that this is safe. As I said before, it's much easier to say that it's safe than it is to prove it. So I have to err on the side of caution. In the general case, it is not safe to multi-write in a relational database. So maybe some questions are coming to mind right now. Why shouldn't I do some of these things? Why can't I write to both masters at the same time for availability? Well, and I'm not saying you can't, but I do say that there is a trade-off potentially here that you need to be aware of. You can write to both masters for availability, but you're going to have to deal with consistency issues on the back end. Now, it's conceivable that you could design your application in such a way that you could just simply take all the writes in both locations, get the writes into one of the databases, and deal with the conflicts later. That might be the case, but I guess I would propose it's not going to scale if customer service has to get involved on every conflict. And might not, especially if they have to go call the customer, right, to work it out. So be careful what you're trading here. Can I increase my write scalability by writing to both masters or multiple masters? So there's a point where this is true and there's a point where this is false. First of all, the point where this is false is that, remember, in MySQL replication, all the data is being copied to all the MySQL servers, all the masters and slaves. So it's being written everywhere. So as you increase writes throughput on one server, that's being applied to all the other ones simultaneously. So in that sense, no, you're not really going to be able to increase your write scalability with multiple masters because all those writes still have to go everywhere anyways. But it is true to some degree in MySQL if you're using row-based replication. So imagine the standard default in MySQL replication today is statement-based replication, where the actual SQL statement is copied from master, applied on the master, copied to the slave, and then rerun on the slave. In that case, the cost for executing that, applying that transaction is about the same. In a row-based replication environment, the master, after it does its write, converts those changes into row-based replication events, simply saying this row changed to this row changed to that, and then that's shipped off to the slave and just applied at that level. The slave doesn't have to reparse the SQL. It doesn't have to do maybe a complicated query to find all the rows it needs to change. It just goes and says, oh, this row's changing, fine. So there is a certain amount of write scalability you can have in that sense with row-based replication, but it's only going to be up to a point. Because again, all those writes still have to go everywhere. What else? Why shouldn't I put all of my MySQL servers in a big ring topology? You say to yourself, Jay, what are you thinking? Dual master is old school. We're going to put all of our servers in a giant ring globally, and we're just going to let replication, we're going to let nature take its course. Please don't do this, because there's a few reasons. The first and foremost is that as you introduce, as soon as you go beyond 2 servers in a replication topology, any of those servers in that ring become a point of failure that breaks replication across the entire ring. So let's assume, say you have 4 servers A, B, C, and D, that A replicates to B, which replicates to C, which replicates to D, which replicates back to A. So if server D fails, then replication might make it from A to C, but it's not going to make it from C back to A. So if you're writing to all of those, the only safe place really to write after D fails is on A, because that's the only way it's going to get to all the servers that are still available. So it introduces a single point of failure, well, actually multiple single points of failure, right? One for each node in the ring. And then secondly, the way that replication works in general is that replication is serialized. So all of the parallel writes that happen on a single master are filtered in sequence down to the binary log on the server, which is then copied and applied in sequence on the slave. Now, if you imagine A, B, C, and D all taking their own writes and also applying the writes from the master above them, all of those keep getting filtered. There's that many more places for replication to lag. There's that many more number of servers that are completely inconsistent at a given point in time. So many people have tried it. It does work, I think, for some people, but many more people, I think, regret it. So do me a favor and don't try to think of a way to make ring topology work for you. And then finally, my favorite. Does an auto-increment offset solve the multi-writing problem? Now, think back to our examples that I gave with the SQL statements. Auto-increment offset solves the first problem. And the way that it solves that is pretty much with a hack. The hack for auto-increment offset and auto-increment increment settings is that you have two masters and you adjust the auto-increments so that, say, the first master only writes even auto-increment numbers and the second master only writes odd auto-increment numbers. So that does solve the first problem. Replication is not going to break in that case. But you've just cut your auto-increment, your total number of auto-increments in a single, well, for a single master in half. And they're also potentially out of order now, which you may or may not rely on. So that, and finally, it only solves the first problem. It doesn't solve the problem of general unique keys being conflicting. It doesn't solve the problem of dual master race conditions where we changed from Percona 1 to Percona 2 and it just went across and didn't really break replication. And it doesn't solve the writes being out of order for statement-based. So these are things that, yes, auto-increment offset does address a certain very small subset of the problems. It doesn't solve the problem as a whole. So, all right, I've made everybody really depressed with the amount of problems there are with multi-writing. What are some solutions, and what are some ways that we can address this problem and make this work in a high or in a production environment, high availability environment? So semi-synchronous replication is probably a good thing to talk about now. What semi-synchronous replication does, and this was introduced in MySQL 5.5, is that designated slaves or specific slaves from a specific master are guaranteed to receive the replication event on commit. Now, I say receive, not apply. So if you understand replication and how it works, there's really two threads in replication. One is a thread called the IO thread that connects to the master and gets a copy of the statements on the master, or the replication flow, whatever is the statement or row-based. And then that copies it to a local log on the slave. And then the SQL thread effectively reads from that log and applies the statements to the database. So semi-synchronous replication only really applies to the IO thread. It only applies to semi-synchronous slaves. It guarantees that those IO threads got the transaction. It doesn't guarantee that the SQL thread has applied it. So multi-writer issues are still a problem here because we still haven't applied the transaction synchronously on commit, and that's why they call it semi-synchronous. So there are still gaps here, still places for that race condition to happen. They just might be a little smaller. Now, this can help remove gaps in a dual master failover because let's just say you're writing to master A, and then master A fails. If you fail to master B, and then right before you actually turn on writes to master B, you wait for the SQL thread to catch up to where the IO thread was, you should have all of your transactions. And I emphasize should. So you shouldn't have any places where data was lost because master A went down. All that data should have made it at least to the relay log on the second master. So it can be helpful there. Now in practice, semi-synchronous replication just really doesn't perform that well. And the reason is because replication is serialized. The binary log is serialized. So what that means is every time it needs to go do a write to the binary log, it has to wait for a round trip to the slave to ensure that the slave receives the message. So it's commit, wait on slave, commit, wait on slave, commit, wait on slave. And your nice master database where you're doing all these wonderful parallel writes, all these transactions happening in different parts of the database all at the same time, highly concurrent, has now been effectively reduced to a serialized, one transaction committing at a time. So that usually is not a good thing for performance. I did a blog post about XtraDB cluster versus semi-synchronous replication in a WAN environment back in about June. And one of the things that I discovered, and it was actually quite obvious when I thought about it, is I had data centers, I was using EC2 instances that were about 100 milliseconds apart. And if you think about it, you can actually tell the throughput of transactions per second on the master just knowing that fact in semi-synchronous replication. Because every transaction has to wait for a round trip before it can do the next transaction, in 100 milliseconds latency between master and slave, you have 10 transactions per second, and that's it. So fundamentally, semi-synchronous replication, not a bad idea, but I don't think a lot of people use it. I do think some people use it, but it's even probably only practical in a WAN environment in most cases. Let's talk about a little bit about single writer and what I mean by that. So dual master, we got two databases, circular replication, but because of all those consistency problems, we're going to make a decision that we're only going to write to one of those database servers at a time. So then the other one is simply for high availability purposes. So if the primary fails, we flip over to the secondary, but we try to enforce the fact that only writes are happening on one of those two at a time. So there's a variety of systems out there. This turns out to be a pretty solid way to do this for the most part. This is a lot of what we did at Yahoo over a lot of years. And there's a bunch of systems that you can take a look at to help you with this. Multi-master replication manager is one of them. MMM, it's sort of nefarious these days, and it's not, if somebody comes up to you and recommends MMM, generally don't. It's not a good idea. There's another one out there called Master High Availability Manager. This isn't so much a dual master, but it is enforcing a single writer in the sense that you have a pool of MySQL servers in general, and then one gets elected to the master, and MHA is capable of changing which one is the master and doing safer change master statements than it is easy with a lot of shell scripts and checking through binary logs and relay logs and things. It can sort of try to figure out what the right positions to change to are. So it's not dual master per se, but it is picking one master, and then if that master fails, flipping over to a new master and then repointing slaves. Percona Replication Manager is actually quite similar type topology. It's a single master with multiple slaves, and if that master fails, we pick a new slave to become the master. The difference here between PRM and MHA, PRM is built on top of Pacemaker, which does reliable network partition management and so forth. All this quorum voting and so forth. It doesn't allow split brain scenarios to happen, which is actually quite easy in MMM. When it does the changeover, it's doing changeover in favor of availability over consistency. So it doesn't have all the logic that MHA has as far as safely doing a change master for the slaves. So there's some discrepancies there, but those are similar type solutions. Tungsten Replicator and Tungsten Cluster you may have heard of. That's a commercial, well, mostly commercial product. The replicator, I believe, is open source. But how Tungsten addressed the problem is that they more or less invented their own replication. So you're still using binary logging, but the Tungsten Replicator sniffs off of the binary log and injects it into its own replication system, applies something called a global transaction ID. It makes up its own global transaction ID. And then if that master fails, the cluster can manage picking a new cluster and just letting the replication flow come from that master instead of the first. And it just simply bypasses traditional replication. So that's a solution that a lot of people do use. And then finally, in MySQL 5.6 or 5.7, whatever they end up calling it on release, there is the Global Transaction IDs feature, which introduces the concept of global transaction IDs to standard MySQL replication. The theory behind this, I haven't had a chance to play with it yet, but the theory behind this is that because you know a global transaction ID, say you have dual masters and you want to change a slave from one dual master to the other, you just tell the new master, hey, I need to start at this global transaction ID, and that master understands what you're talking about. In practice, I think there's some Python scripts involved, but I'm not entirely sure. So, but at least in theory, this should help us make the change masters in MySQL replication a lot easier and more deterministic to do on a failure, which I think is great for replication as a whole. And then another solution that it probably doesn't come to many people's surprise that I would talk about this is Percona XtraDB cluster, also known as Galera, which XtraDB cluster is Percona server with the Galera patches installed. Galera is synchronous replication. Well, let's just say, first of all, it's not standard MySQL replication. It's its own replication mechanism, kind of similar to Tungsten in that way, but it's doing a much more synchronous replication. Now, it's not fundamentally truly synchronous, but I don't want to spend a lot of time on that here. The idea, though, is that we do writes on any of the nodes. The replication mechanism works to prevent conflicts for those writes on all the other nodes, and then the data is written to all the nodes, much like semi-synchronous replication does in standard MySQL. So you write anywhere, read anywhere. It still doesn't acquire locks on all those nodes, and it handles those locking conflicts in a special way. It's sort of the secret sauce of Galera that makes it work. I can talk at length about Galera, but that's not the focus of this talk, so I don't want to get sidetracked here. So my summary. No distributed system behaves just like the standalone equivalent. I think one of the problems that we face in production distributed environments is that the developers are doing all their testing on a single development MySQL database, and then as soon as we get to 10 databases with replication lag or using some clustering technology or whatever, it starts behaving differently. Now there's always trade-offs in how things should work, and once you start moving to a distributed environment with high availability solutions and different requirements and constraints that you're placing on the system, there's always trade-offs that you have to take away from to make those things work correctly. And certainly the holy grail is a globally distributed, non-latency, there's no latency involved, where you can just write to all these SQL databases around the world everywhere, and it magically synchronizes everything up behind the scenes, and you don't have to do anything. I think the reality is that in the relational model, that just doesn't make any sense. You can't take those benefits without having some other cost. And the cost would probably be very expensive application logic to resolve conflicts, for example. You can't do it at the generic level. Single writer in not just MySQL, but pretty much any data store is almost always the most application-friendly method to handle writes. So if you have an existing application you need to take from a single database server to multiple database servers or dual masters or even XtraDB cluster, it's almost always the case that just writing to one of those nodes, even if you could technically, in theory, write to many nodes, it's almost always the case that single writing is better, even in XtraDB cluster. It's just a fact. Multi-writing is usually, but not always, the exact opposite of application friendly. So be careful with that and how you decide to do things in terms of deploying to production. So with that, that's pretty much all I have for today. I'm, I guess, ready to take questions now. Terry will relay them to me over voice, and I'll try to answer them the best I can.
Okay, thanks, Jay. Again, if you have questions, anyone, please enter them in the questions box and the go to webinar screen. First question we have is, what are your thoughts on using AI with even and odds for respective masters?
I think I covered that. AI being auto-increment offsets with even and odds. Again, I think that only addresses the problem of auto-increment collisions. It doesn't address other unique keys collisions. It doesn't address the potential for race conditions across masters, and also the statement reordering. So, it's only really a limited set of things that it addresses and sort of ignores the rest.
Okay, good. From which master would you replicate from in a multi-writer situation?
Good question. It really kind of depends on the requirements, in my mind, of what you need to do with those slaves. So just to give you an example, in the Yahoo environment where we were almost always putting these masters into multiple data centers, then it usually made very good sense to have replication slaves off of both masters so that we could always read locally in the data centers. But it also made sense, at least in each data center, to have one other server, one other slave that replicated from the remote master for the purposes of rebuilding. So if the primary master, if the master in the data center failed, we could use that slave, the slave that also replicated from the other master, as a way to rebuild the local master, or even fail over to that slave in the data center. So it kind of depends on what your purposes are, but that is another sort of sticky point of this whole thing. You may have high availability at the master level to be able to flip over from one to the other, or to write to both. But then, one of your slave, the slaves that you hang off of one master is always going to be one hop further away from the other master. And if one master breaks, all of the slaves that are associated with that master are now also disconnected from the other master and unable to be in synchronization. So there's a lot of sort of pros and cons that you have to work through to determine, what the best, most ideal solution is. At Yahoo, for us, it made a lot of sense to sort of split those up 50-50. Half the slaves replicate from one, half the slaves replicate from the other. But in your environment, it may not be effective to do so.
Okay, next question. How do you block the DDL statements like drop database statements to copy over to a slave or another master?
How do you block DDL statements? Well, so in the replication, with standard MySQL replication, you can use a session variable called SQL log bin. You set that to off, and that basically says anything that you do in that session doesn't get written to the binary log on the master you're on, and therefore doesn't replicate. However, what you have to be very careful of, particularly in a circular replication environment, is that if you do any kind of schema change that renders replication incompatible, so for example, you drop a column that the other master, say somebody's writing on the other master and updating a column, and then you go drop that column on the second master, then that, of course, is going to break replication. So in terms of keeping DDL that doesn't cause replication incompatibilities, like say changing indexes or maybe adding or removing an unused table, those are all should be fine to do one at a time. But for more online changes, you may want to look at things like using PT online schema change and so forth to do the change on all of the masters and slaves more or less at the same time.
Okay, next question. Is point table checksum only for master-master replication, or is it also useful in a master-slave replication for HA?
PT table checksum is useful in pretty much any replication topology environment. So master-master or master-slave. Certainly in master-master, if you are going to make the choice to multi-write, then PT table checksum would be invaluable, I think, to start detecting where some of those race conditions come in, where replication doesn't break, but you can start to get slave drift. But even outside of that case, PT table checksum is very useful for just master-slave. So say there's some reason why the slaves are drifting. Maybe somebody is misbehaving at the application and they're connecting and writing on the slave. Maybe there's some non-deterministic way that the replication is working and that's causing data drift on the slave. Usually that's the case for statement-based replication that can creep in. Replication between major MySQL versions, sometimes that can cause data drift a little bit. So PT table checksum is really designed to be used for pretty much any replication topology, and it should work fine in a master-slave and also a dual master environment. And I also will add it does have early support for XtraDB cluster, but mixed replication topologies with MySQL replication masters and slaves and also some clusters thrown in there is a little complicated, and we're sort of still working out how it should work in those cases, because there's the case where we want to compare it to other asynchronous masters and slaves, and there's cases where we want to compare all the nodes in the cluster to each other. And those are kind of different. So, but yes, PT table checksum is very versatile and very powerful for all of those things.
Okay, next question. We're using DNS failover with each server hosting web and database with dual master. Are there any potential problems with this configuration?
The problem with DNS is that it does not give you a nice point-in-time atomic failover. And what I mean by that is that DNS entries, by definition, have TTLs, and those TTLs are cached by resolvers until, and then once they expire, then they come back to the authoritative DNS server and re-look it up. So let's say you have a DNS TTL of a minute, which is actually pretty fast by most DNS standards. So if your application failover, there's also a couple of cases here, right? You could use DNS for your website application failover, or you could use DNS for your application to database failover. But let's just take the first, because I think that sounded like what you were talking about. So you have your web server. It runs on one server. The IP or the DNS is pointed at the IP for that server, and then you change it. There's going to be a window of time while all of those TTLs are expiring where some clients will still have the old IP, and some clients will be starting to get the new IP. And then the question is, how do you manage that at the database layer? So let's just say you use circular replication between the two servers for MySQL replication. So if that's the case, there's going to be a window of time while the DNS is transitioning where you are multi-writing. Now you can control that by, for example, having a flag in your application so you can turn off writes. So let's say your standby server that you're failing over to, you can fail over to it first with writes completely disabled and just running your website in read-only mode, for example. You can also control that at the database layer. You can set the read-only flag at the database layer, but that, of course, only applies to non-super users, so be careful there. But and your application may just break if it tries to write and it gets a read-only error. So those are some ways to kind of control the failover in a DNS-based failover situation. And I think that's okay for sort of just a two-server, fairly simple setup, like just one web server and database to another web server and database. Once you start getting into a larger environment with more servers, a more complicated failover, then it probably makes better sense to split up your tiers so that your website failover and your database failover are different things. And then even a step further to say, well, your database reads and your database writes are actually also separate things and separate failovers and so forth. So, for example, a standard Yahoo topology would be a failover, DNS-based failover for hardware load balancers in multiple data centers for the web servers, and then at the database layer, there was a more atomic internal mechanism we used to flip over from one master database to another master database, and we also used the read-only flag to control that. So all of the reads in a given data center for web servers hit the local slaves in that data center, but all of the writes went through this mechanism and only went to one of the two masters and one of the two data centers, and that failover was very controlled and very as atomic as we can make it. So it's a pretty complicated question. There's a lot of facets to that, but I think my big concern about DNS for database failover is just making sure you're not allowing writes to happen on both places at the same time, if you can avoid it, because all of those potential problems I described will happen during that window.
Okay, next question. For slave-only instances, is there a way to set a delay in copying the stuff?
For slave-only instances, is there a way to set a delay? Okay, so essentially I think they're asking about having a slave that has an enforced set of lag. To say, well, this slave is always an hour behind or a day behind or something like that. That is possible. I believe that's actually being built into the semantics in replication in MySQL 5.6, but it is also available today in the Percona toolkit. There's a Percona toolkit tool called PT slave delay, and it does precisely that. You run it on the slave, and it enforces that the slave it's not super precise because it has to do polling, but it will enforce that the slave never gets caught up more than, say, an hour, and then it will never get lagged by more than, I don't know, say an hour and a half. I mean, there's a way to sort of control that window. But that's a tool that you could use to enforce lagged slaves if you want to do that. The standard use case for lag slaves is to have just a quick online backup protection for database admin fat fingers, is what we call them. Where, whoops, I typed drop database and I meant drop this unused table, and now your production database has just dropped. You can go back to the delayed slave and have a quick restore to an hour ago or half an hour ago or whatever you choose.
Very good. Thanks, Jay. And just to wrap up, I wanted to point out a couple other opportunities coming up. On November 28th, we'll have another webinar, a joint webinar with Continuant. We'll be talking about tungsten, so please feel free to join us for that. Also, for those of you in Europe, Percona Live London is December 3rd and 4th. And if you'd like more information there, please visit percona.com/live. Jay, thanks for today's webinar, and again, we will be sending out a link to the recording from today's webinar along with a link to Jay's slides within the next 24 hours. Thanks, everyone. Have a good day.